So for problem number one, for having the resistor, I use Kirchhoff's law, because if you use Ohm's law, it won't consider the LED in here. So we use E minus BS plus B1, that is from R1, and minus B2, that is the voltage in the LED. So in this, I did two cases. In the first case, I use the B1 as the least amount of the resistor, and then another one for the highest resistor value for the LED. So we had the value of 305 and 345, but if I use, as the problem says, the middle of the voltage, we have a resistor of 330 ohms. For number two, we cannot use only the 320 ohms. Then we have a problem, because it is not enough for our LED in the mid-range of the voltage, but it can be used if we use my values that I had for the one from 3005 to 305 to 345. And here we know that the rule for sum of resistance, for equivalent resistance, since our circuit is in series, we can have a sum of all the resistance to have an equivalent resistance. So in this case, we have the case of 330, and using these two resistors can be used if we have not the mid-range of the resistor, but maybe the minimum, or the minimum, that is 305. So now for the second situation, and the variables that we need to consider to guarantee our maximum energy from the defibrillator is that our capacitor needs to be fully charged in the least amount of time. So in order to have this, our resistance have to be not that high in order to have a capacity fully charged in the quickest time, but also not having in the limit that it would damage the capacitor. So we need to consider here the formula of capacitor discharge in also to do that. Also, I investigated that the defibrillator has an inductor in the output circuit. So this inductor gives the optimum shape and duration of the delivery current. In the motor and defibrillator that has a higher range, the effective energy requires for defibrillator is less in smaller capacitor. So that's another opinion. And we have here a graph of the defibrillator, that we have a capacitor, and here we have a resistance in order to not damage this capacitor. In order to guarantee that the defibrillator charges in 10 seconds at most, we need to first have the total resistance, or the resistance equivalent, and also the capacitor and the equivalent capacitance, in order to have these two values and obtain tau, that will be like the amount of times we will have for the defibrillator. And also we need the voltage power in order not to have this data and have our formula resolved. Now, in order to have our maximum current, we need to have an equivalent resistance, again as the past problem, as low as possible. Here we can see that the formula of the current, depending on time, will vary between the value, with the value of R. And if R is lower, more current will flow from the capacitor in less time. So as we see in the formula, it depends from the resistance. So now to determine the power of a motor defibrillator, using the minimum energy in the range, we need to we use the formula of power having the watts, that in this case the delivery is from 150 and then divided into the 0.02 milliseconds. And we have a total of 7,500, and that will be our value in order to determine the power. And for number 5, the two factors that can prevent the heart from receiving an current will be, again, time. If the time is higher than the previous value, of course, following our formula, power will be less. So it will prevent the heart from receiving enough current. Since we have another formula for current, that current is power over voltage. So if our time is less, our power will be less and affecting the current formula. And again, our second factor will be voltage, since again our current depends on our power divided by voltage. So if the voltage is lower, our current at the end will have least value, a lower value at the end.